Question number 30. In this question 30, they have asked about, they are defined in very complicated terms something which is similar to an expenditure function. So let us go by this definition. So they say that given a non-empty set C which belongs to Rn, so C which is a subset of Rn, so you can think of C as an indifference curve. Okay, so C is basically a subset of Rn. Rn is the consumption set, and as a subset of the consumption set Rn. So Rn is the consumption set of which C is some indifference curve. Then in this subset C, P belongs to Rn plus. So think of P belongs to Rn plus. So think of P as a price vector. Okay. Then what they say is for every P there exists a C of P. So C of P such that P dot C of P is less than P of C for every. So think of C of P as Hicksian demand. So you have to think of C of P as a Hicksian demand, and E of P which is equal to P dot C of P. So think of this as expenditure function. So what they've basically asked you to show is that the expenditure function, what is this expenditure function? Is it linear? Is it concave, convex, quasi-convex? What is it? So remember this property of expenditure function, the property which we have done in class as well is that expenditure function is concave in prices. So expenditure function is concave in prices. So this is what they have asked the proof of. Now if you remember this property, it's mentioned in almost all textbooks which talk about concavity of preferences and all those stuff, convexity of preferences and stuff like that. If you remember it, then great, you don't need to prove it, because this is essentially the defined expenditure function. They have asked the property. But if you don't, then even in that case, I mean, I would not recommend going about the proof, because if you don't know it, then you have to find a proof for each and every one of them, because you don't know how to go about it. So in that case, I'll recommend maybe leave it to the at the end, because proving it is going to be time consuming. So if you don't know this property, then better leave it for the end, because it's going to be time consuming. Because right now I know that it's concave and I'm going to only prove that it's concave. But if you don't know it in an exam, you have to essentially check for proof of each and every option, which is going to be very time consuming. In any case, so I'm going to show here through a proof that expenditure function is concave in prices. So what does it mean for any function to be concave? So this is not the definition of concavity in double derivatives, because that won't work here, because price vector is not what do you call it? Price vector is a vector, so it's not a single dimensional function. So we cannot use double derivatives here. So the property that you have to use here is the general property of concavity. That is, suppose that this is my P1, this is my price vector P1, and this is some other price vector P2. This is P1 and P2. Then concavity of this curve implies that at any midpoint between these two price vectors, that is yeah, at the midpoint of these price vectors, that is p vector, which is equals to lambda p1 plus 1 minus lambda p2. Okay, so if I take any intermediate price p bar, which is equal to this one, then what I can say is that the expenditure function value at this p bar, this is expenditure function value at p bar, it should be greater than the averages of these two expenditure functions. So this is going to be lambda times e of p1 plus 1 minus lambda times e of p2. So what we need to show is that is expenditure function at lambda p1 lambda p1 plus 1 minus lambda p2 must be greater than or equal to this particular value. Okay, so this is what we need to show. So let us start with any p1. So let p bar equals to lambda p1 plus 1 minus lambda p2. Okay, then p bar dot e of p bar is basically lambda p1 plus 1 minus lambda p2 times dot product of e of p bar, which is basically lambda times p1 dot e of p bar plus 1 minus lambda times p2 dot e of p bar. Okay, so let me remove this particular thing. Now notice that p1 dot e of, so the property says that for any price vector p dot c, oh no, sorry, not e, this is c, sorry, my bad, p dot c, e is p dot c, so I'm writing in dot product terms. Yeah, coming back, the property says that for any price vector p dot c of p should be less than or equals to p dot c for any other case. So for p1 dot c of p1 should be less than p1 dot c of p bar. So this should be true for p1, and for p2 dot c of p2 should be less than or equal to actually p2 dot c of p bar. Okay, so substitute this in substitute equation inequalities 2 and 3 in 1. So what I get it from 1 comma 2 comma 3, what I get is that p bar dot c of p bar should be greater than or equal to p1 lambda p1 dot c of p1 plus 1 minus lambda p2 dot c of p2. Now this is nothing but expenditure function at p bar. This should be greater than or equals to expenditure function at p1 plus 1 minus lambda times expenditure function at p2. So expenditure function at lambda p plus 1 minus lambda p2 should be greater than or equals to lambda e of p1 plus 1 minus lambda e of p2. So that's what we wanted to show, that's what we have shown. So this implies that expenditure function is concave. Okay, so that completes the proof.